Swayam Prabha. Digital India. Educated India.
The last lecture we were discussing the use of offsets, and we had seen that how we can effectively use the offset to take care of many situations in which you can have much better efficiencies by using this method, which is only a method of application and changing your layout. One thing which I'd like to point out here, that by the use of this offset, it can also make a lot of difference in terms of your parameter selections or in terms of the design of the system. You can get much more flexibility of the design. For example, the minimum overlap which is recommended parallel to the main line as 6 meters. So in sprinkler irrigation design, you must have at least 6 meters of overlap in terms of the overlap on the wetter diameter. Knowing the wetter diameter, you must have, for the design to be acceptable along the along the main line, you must have at least an overlap of 6 meters. But by utilizing the offset, when you use the offset, this limit can reduce to 3 meters. This overlap in the case of offsets can reduce to 3 meters. Now this gives you a lot of flexibility in terms of if you have a situation where your DW requirement is coming to be very large. Now by using the offset, you can take a DW which is, or you can make the selection of the nozzles in such a manner that a DW which is lower than that level can also be made use of. So from that angle, you will get a lot of flexibilities by using the offset procedure. And it also, the use of offset also enhances uniformity that we have seen in the last lecture. We had taken up the situation where we had seen that how the uniformities can be enhanced by the way we make the applications by creating that offset and locating the position of the lateral. With that, we'll go to the next element, which is the irrigation interval. Now, irrigation interval is a very important element in the design. What do we mean by the irrigation interval, first of all? The irrigation interval pertains to the time which is available for applying the irrigation. If you have an area, let me take any one area. If you have an area, now you are irrigating the total area through some system. Now you have different options available. As a designer, you have different options available. You might run a main line and then try to irrigate the area through two different settings, half the area in one setting, half the area in another setting. You also might try to divide this into three components. Now, whether I divide it in one component or the two components or three components, this decision makes a lot of difference in terms of the total equipment requirement. If I want to irrigate the total area in one go, I'll need more equipment. It's not just the equipment also. I might need different discharges. I might need different set of all those parameters which can take care of this combination. But that question is something different. Right now we are trying to look at the irrigation interval. From the irrigation interval point of view, if I have the total area divided into three compartments or three separate sub areas, First, I irrigate this area, then at number 2 setting, I irrigate this area, number 3 setting, I irrigate this area. And then again, I come back to the previous area. Now, how much time I have taken in irrigating each of the area and how much time has lapsed in total between the first irrigation and the last irrigation? We have to look at that lapse time. Is it a time which cannot be, this area cannot wait that long by the time I come back to this area? If that is the situation, then your irrigation interval is much larger than what is the desirable interval. Your irrigation interval cannot be of such a length where the soil moisture reaches below a specified or a desirable level. So if your irrigation interval is going beyond that, that means you have to do something to ensure that you are irrigating the whole area in such a manner that you are able to come back to the first area where you started with within a period which is the desirable period, which you can delay the irrigation, or you can use the second irrigation after that much period, and that will be a function of the climate. What is the rate at which the water is getting lost from that soil zone? So all those things we have to look into it and decide accordingly how the parameters have to be set. So when we say irrigation interval, what we mean is that what is the duration of the time which we can use for actual application of the water. Okay. And the irrigation interval, to arrive at the desirable irrigation interval, you will like to find out what is the total allowable depletion. It will be a function of total allowable depletion, which in turn will be a function of these quantities. What these quantities are? TAD we have dealt with earlier as the total allowable depletion, and let's say this is expressed in millimeters. TAM as the total available moisture, and the total available moisture is the depth per unit depth of the soil, so millimeters per meter depth of the soil, and the MAD as the management allowed depletion. This is something which is a prerogative of either the management or the farmer, and this is expressed in fraction, whether you will deplete 50% of the available moisture or up to 60% or up to 40%, that is what. And dr is the depth of active root zone or effective root zone, and meters. Now, knowing the total available moisture, which is a function of the soil type, knowing the management allowed depletion, which is a function of again it depends on the crop type, how sensitive the crop is. We have seen all these things, and depth of root zone we also know. So, knowing these individual quantities, you can find out what is the total allowable depletion, how much deficit can be created in a particular soil with respect to the crop which you have. The TAM normally, the total available moisture is the difference between the field capacity and the CW, which is the limit of crop extractable water. So, CW you can say is the crop extractable water, millimeters per meter. This is also the field capacity, and millimeters per meter depth. Now, the TAM, as we have just said, that is a function of the soil type. For light sandy soils, the TAM is around 80 millimeters per meter, sorry. And for medium soils, all this is available in literature. These values are standard values, might change when you have more elaborate soil classification. Similarly, the MAD values, again, as we just mentioned, that depends is a function of what type of crop is in question. If you have high value crop and as shallow rooted, MAD is around 33%. So the level of extraction is much lower when you have more sensitive crops. When you have medium value crops, medium rooted, you can go up to 50%, and for low value crops, normally deep rooted, the management allowable depletion can be as high as 67%. These are some of the values which are order of magnitudes, not literal values. They can change from situation to situation. But in general, you'll find that the deficit which you can create, which you can afford to have, will be much less if your value of the crop is quite high, and it can go up if the value of the crop is low, because is attached with the yields. How much the yields will be affected because of these higher deficits, because if you create higher deficit, there will be more stress in the crop. Whether the crop can take that stress or not, that is the question. Now the irrigation interval is basically, now if we say that Ti is the irrigation interval, is nothing but total allowable deficit by what is the rate at which this deficit is being created, or if you say that this is the availability of moisture, because that is what you like to replenish, and then at this rate this is going to be lost. This ET crop is the peak period crop water requirement. This is peak period crop water requirement, and millimeters per day, and this quantity is in millimeters. So you will have Ti, the irrigation interval, in days. So this basically shows that how long you can wait for the next irrigation, and that is dependent on at what rate the crop is utilizing the water and how much water is available. TID is we are basically saying the total allowable depletion. So this is the moisture which can be extracted, which can be allowed to be extracted, and that moisture is depleting at this rate. So you can get a value of the irrigation interval which is permissible. Now it's not necessary that you have to complete the irrigation in that period. You might decide, as that is again a management decision. That is a decision which is dependent on you as a irrigator or as a farmer, how much time you want to utilize for the irrigation to be completed. But it cannot increase this period, the irrigation interval period. You must complete the irrigation within this interval. It can be much lesser than this. But when you try to reduce it drastically, then to apply that water quickly, you will incur other problems. So you might not be able to for the design to be better, for the design to be economical, you will find that you might try to be quite close to this irrigation interval which is available to you because of the various other reasons which we will just look at as we go further. Then comes the aspect of nozzle selection criteria. Now, this is a very important aspect in the sprinkler irrigation design, because this is the main thing which is deciding most of the other parameters, because the selection of this will influence almost all the other parameters, whether it's the rate of application, or is the discharge, or is the pressure, or is the wetted diameter. All those things are interdependent, and even the spacings, because all those, the spacing also is a function, or is dependent on which sizes you are using, and what will be the distribution pattern, what will be the wetted diameter. All those things are interrelated. So if you look at this, the background of this, the nozzle selection, let me give you some of the statements which will give you the interconnections which are there, or the dependencies. That if we have a nozzle operating at low pressure, this will result in low operating costs. If the pressures are low, the operating costs will also be lower. Is quite understandable. But if you have a lower pressure nozzle, what is the impact of this? Selecting a lower pressure nozzle, the impact is that you will have smaller wetted diameter, as well as lower discharge rate. So after taking this step, you have landed yourself into this result, that by selecting a lower pressure, you have reduced the wetted diameter, you have reduced the discharge rate also. Similarly, if you select a particular type of the nozzle, now the nozzles can be sprinkler heads with a single nozzle, they can be sprinkler heads with double nozzle. So let's say that if you select a single nozzle sprinkler, what is the result? May be that it will have a lower uniformity coefficient, but at the same time, under the wind conditions, it might be quite effective. So it might perform, or it will perform better under wind conditions in comparison to the double nozzle sprinkler. Whereas the double nozzle sprinkler will have higher uniformity, That will be under normal conditions. Now this higher uniformity is because of the increased discharges. So in this case the discharges will also be higher in the case of double nozzle. So they are, when you choose one thing, there will be some plus points, there will be some minus points, and that is where is important to understand that the nozzle selection procedure is a very iterative procedure. It has pros and cons. So you have to make a selection and then see for the various indicators, the various constraints, whether they fulfill all the constraints or not, and accordingly make the choice. You might have to come back to the various levels, make a selection. If it's not satisfying your criteria, make another selection, and then ultimately select one which satisfies most of your conditions. So is a trial and error, is a balancing approach that is important to understand. But the general criteria which you must look into when you make the nozzle selections, these criteria are that the discharge should be high enough, to meet gross application rate requirements. Now you know that what are the gross application rates. We have even looked at a table which we had formulated where we had given the gross application rates which are desirable rates under the specific conditions. So you should intend to choose those nozzle sizes which have the discharges which are high enough to meet this criteria of having the gross application rate satisfied. The net application rate, because gross application rate takes into account the evaporation and the drift losses also. That means the amount of water which is coming out of the nozzle should be at least taken care of by that selected nozzle. But when you come to the other side, the net application rate, you have a criteria which is just diagonally opposite. The net application rate should not exceed the intake rate of the soil. That means you have a constraint on both the sides. On one side you are saying that the gross rate must be sufficient to take care of the application and the gross application rates. On the other side, it shouldn't be very high so that the net application rate becomes such that it produces the surface runoff. So you have a close range to play within, and that is where the nozzle selection becomes a very important aspect. Similarly, the selection of the nozzle in terms of the rate of application or the discharge, which is prevailing discharge, it should be let me say Q should be sufficient to apply net irrigation. Now comes the question of how much time you are taking to make the same application, which is related to your irrigation interval. Q should be sufficient to apply net irrigation within the operating schedule. Now you cannot select a nozzle size which has such a low discharge that when you talk in terms of the time taken, it should exceed the total setting or the total irrigation in the total area under your interest. You exceed the irrigation interval. So that is another constraint put on the nozzle size, because this, so the discharge will also be a function of the nozzle size, along with the other things like the pressure and those things, of course. Then you have another requirement that the wetted diameter must be compatible with the spacing, the main line spacing and the lateral spacing, and the main line spacing. Because again, how much wetted diameter you are going to have is a function of the nozzle selection. It is dependent on the nozzle. And the spacing, you have to have a compatibility between the spacing and the wetted diameter, because we have said that there should be a minimum overlap of 6 meters. Now that overlap of 6 meters will come only through the overlap of the wetted diameters, and the overlap will be decided also by the spacing which you have utilized. So this spacing is also related with the type of nozzle which has been selected. Now as a result, you can now appreciate that the nozzle selection is a very iterative, it has to be a very iterative process, is very can be subjective also, because there are many sizes of nozzles which are available. Which one you decide, it can be, they can be quite close. If I give the nozzle selection to 3 different people, they might come out with some nozzles which are keeping track of all their requirements, or within their setting which they have decided on, because all these things can change drastically the way you are going to operate the system. So you cannot standardize these things. They are highly subjective, but from that angle only, all these constraints have been put, they have been made elaborated through various different criteria, so that you force the designer to be within those constraints. And with that thing in mind, there are many tables which have been developed to help the designer in looking at or in picking up these proper design parameters. And the tables, I won't give you the tables here, I'll just tell you that what type of tables are available, what are the various parameters which they are utilizing. For example, there is a table which gives the wetted diameter in meters for different under different pressure, the nozzles of different diameter. So for different nozzles running under different pressures, you have their wetted diameter. How the wetted diameter varies, because if you want to select a wetted diameter which is a desirable wetted diameter, you can use this table. There can be another table which give you the discharge and liters per second, and it's the other parameters are the pressure and then nozzle diameter, as you have in the case above, the table above. So for different, for example, I can give you the values of some of the nozzle diameters. The range can vary, and this is from 240 kilopascal to around 380 kilopascal. So you have the discharges which are under these conditions. What will be the discharge available? Similarly, there are many other tables. There is another table which give you the average gross application. Now, all these tables will be available in the resource material. The average gross application dg in centimeters per hour. And this table discharge per nozzle, the discharge per nozzle is known for different nozzles in liters per second, and these discharges vary from 0.126 liters per second to 0.631 liters per second. Now, depending on this data plus the sprinkler spacing, which is the mainline spacing and the lateral spacing, for different combinations of spacing. For example, this table gives this in meters. For different combinations of spacing and for different discharge per nozzle, what will be the average gross application which you will obtain? It gives the information on that. You can make the selection directly, whether how much gross application, average gross application you are getting under those circumstances when you select a particular nozzle. So that way there are many such aids which have been provided for making the designer's effort quite minimal, and the designs can be taken up quite quickly. But the fact remains that this is a very specialized job, in the sense that you must understand what you are doing. Once you understood the thing properly, then there is no problem. You can make the designs without any big problem. Let's take one small example to just go through how we make use of whatsoever we have gone through so far, how we actually make use of those details or those elements which we have studied so far. In an actual case, we'll take a very small case where we have some available data and how we can make use of that available data along with the various conditions which we have imposed to come out with a relevant and a proper design. The data given is quite elaborate. We are assuming that we are using a side roll system. The climate of the region is warm maritime. The peak crop period requirement 80 crop is known to be 7 millimeters per day. Then you will need some meteorological data. And the meteorological data, this pertains to the peak period. And the meteorological data is given in the form of the maximum and minimum temperature. The minimum temperature is 10.5 degrees centigrade. The maximum temperature observed is 27.8 degrees centigrade. Now, this you can obtain the average temperature over the day is 19.2 degrees centigrade. Similarly, the other meteorological variables which are available are the maximum relative humidity, it's 93%, and the minimum relative humidity is 39%, which again gives mean relative humidity of 66%. Then you have the wind speed at 2 meters height is given to be 6.4 kilometers per hour, or if you want to convert that, you might need it in meters per second, 1.78 meters per second. Besides this basic data, there are some other data which are relevant and which are required for the design purpose. They have been taken accordingly. The total allowable depletion is 82 millimeters, and maximum application rate let me call it Y max is 0.76 centimeters per hour or 76 millimeters per hour. Then along with this, you have the design constraints. The design uniformity which is desirable is 85%. And the adequacy level is 90%. Now these are the various data available. There is one more segment of data which is available, that the spacings which you will like to have is dependent on what type of equipment you already have available with you. So from that angle, the mainline spacing should be either 15 meters or 18 meters, and the lateral spacing should be 12 meters. These are very realistic constraints, which will be normally you will feel that they are there because of the way things are. Either the farmer is already having some equipment, so he wouldn't with each design he wouldn't like to buy new equipment. There might be some flexibility in terms of he has two different types of pipelines, or what are the pieces available, how he can join them. All those things are equally important. Now, besides this basic data, there are some constraints on the operations also. So on the operations side, the constraints which are there, they are: the system is to run a schedule of 9 out of 10 days during the peak period. Furthermore, the operating time is 20 hours out of 24 hours. Now, it's quite likely that out of the 24 hours, the 20 hours are kept for operation. The remaining 4 hours are for moving the pipelines and those activities you need to have some time, which will be the time when the system won't be running. It is also advisable to run the system. It is desirable that the system should run on operating pressures which are minimum. Now, this will reduce the operation costs. So the operator wants to run the system on the minimum possible pressures, operating pressures. Another constraint: use single nozzle sprinkler head. Now, based on this data and based on all the desirable constraints, you have to design the system. When you say you have to design the system, what you'll design it for? The design should include the selection of nozzle dia. What size of the nozzle should be used? What should be the operating pressure? What should be the wetted diameter? The nozzle discharge. As once you have found out selected the nozzle diameter and the operating pressure, the nozzle discharge can be known. But you are interested in knowing the nozzle discharge also. You are interested in finding out the gross application DG and the actual time of operation. We had said that we will try to confine our time within the irrigation interval, but the actual time of operation can be much lower or it can be within the irrigation interval. How much will be the actual time of operation? That is what we have to find out, and that will be a function of what are the other parameters which have been selected. I think we'll stop here because we won't be able to finish the thing within the remaining time. I'll give the answers to any questions if you have. Okay. So we'll take up this exercise in the next class.